Now moving on from the density of water to why water is such an excellent solvent, meaning it's really good at dissolving things. Because of its polar nature, water can form hydrogen bonds with lots of things, and therefore it can dissolve a lot of things really, really well. So let's look at this example with salt crystals that are placed in water. Salt crystals are typically made up of sodium chloride, which are represented by NaCl, okay? So sodium chloride. But when salt crystals are placed in water, water molecules surround individual sodium and chloride ions that have broken away from the salt clump. Now, sodium ions have a more positive charge, so the more negative end of water molecules, meaning the end with oxygen, surround the sodium ion, forming a hydration shell, keeping it from reassembling with the rest of the salt crystal that it broke from. This is the basis of dissolving. And similarly, chloride ions, which have a more negative charge, also have a hydration shell form around them, but because the interactions with the partial positive ends of the water molecules, meaning the hydrogen ends of the water molecule. This is a prime example because salt, or sodium chloride specifically, is a polar and therefore hydrophilic molecule. So it dissolves readily in water because it has a high affinity to interact with molecules due to its polarity. However, water still has significant impact on molecules even if it can't dissolve them. Let's explore a non-polar molecule like oil. When oil, a non-polar hydrophobic substance, is placed in water, the oil droplets all aggregate or cluster together, avoiding the water molecules. We call this clustering of non-polar substances together when placed in water hydrophobic exclusion. So even though water doesn't directly interact with nonpolar molecules, it does still influence them. And as you'll learn later, the ability for water to influence the shape of something can very easily alter that item's function as well. So now, as another check-in number 21, would you expect the following molecule to be hydrophobic or hydrophilic? Think back to polarity to help you out. Number 22, would you expect this molecule, potassium chloride, to be hydrophobic or hydrophilic? Number 23, below is something we call a phospholipid, which is a substance that makes up the protective membrane surrounding all of our cells, right? If you've ever heard of a plasma membrane, it's made up of these guys. These structures are made up, though, of a hydrophilic head and hydrophobic tails. Considering the properties of water, along with the concept of hydrophobic exclusion, how would you expect a bunch of phospholipids to arrange themselves if you were to dump them in a pool of water? Number 24 and 25. When you go swimming in a lake, you are submerged in and surrounded by water. Yet your body does not absorb all the water that's surrounding you, right? Based on this, do you think your skin is likely hydrophobic or hydrophilic? Number 25. Why do you think this property of your skin is so important? All right, A+ work, everyone. That concludes our discussion on the properties of water, which finalizes our discussion on this portion of the chemistry of biology. Awesome work!